So the first thing you want to do is you want to install Python pip, because Python pip is an installer package using which we're going to install everything else. And Python pip is an installer package which installs packages that are written in Python. And pip is an archive where all these things are stored, which you can download and install from. The next thing you need is Git, because we're going to use Git to, And here's the toolbox for those of you who didn't see it yet. It's at the end of the course website, or you can just simply go to this link, or I think a shorter link would be this. And there is an installation guide. This is basically what I'm going to do right now. So once Git is installed and once Python pip is installed, you can install the toolbox by saying pip install, clone it from the Git repository, which is in my repository. Sorry. So all you need to do is run this install command, and it will clone, it will download, it will set it up on your path. It will also install other packages that you need for this toolbox. It will install NumPy, SciPy, Matplotlib, and pretty much anything else that you need. So you can see that it first installed Theano and then it's installing NumPy. So the toolbox is written on top of Theano. Although it is written on top of Theano, to use this you don't really need to know how Theano works, but it's good if you know how Theano works. Theano is one of the top frameworks for deep learning today, alongside Lua, Torch, and TensorFlow. Oh, okay. So there's something wrong with the NumPy installation. While this is happening, I also want to remind you that I extended the deadline for Mini Project 2. It's due on Tuesday, I think on 14th, and the project proposal is due next week. Mini Project 3 is also due next week. There we go. So that's it. It's the installation is done and your machine is ready to start with Mini Project 2. So how do you verify that the installation is good? You open your Python and then you see if you can import the toolbox, and when you do, just check if the version is the first alpha version, and that's the version that you should be using. That's pretty much going to be the version until the end of the class, I think, until I start installing writing code for Adam, which I haven't done yet. So now that this is done, this center of this is how the Yann toolbox is, the network class is structured. There is a class called, can you see this figure at all? There is a network object, and the network object has some methods and some properties. Methods include adding modules and adding layers and cooking the network, which is equivalent to estimating the backprop and creating the backprop network, training, testing, and validation. The properties of the network include layers and different kinds of optimizers, data stream, and all those modules. And I'll tell you what that means in a sec. So the beginning of anything in the toolbox is you need to import the network class, which is in the network module. And once that is done, you can create a network. So this creates a new network, and The network has no layers, it has no optimizers, it has nothing right now. And that's it, the network is now created. So the first thing you need to do is also have a data set to work with, because everything on your network starts with the data. That's the first layer you want. This Toolbox also has capabilities for creating all kinds of data sets that we'll use in this course. So let me create one. So this module special has wrappers for creating all these data sets in a quick way. So I'm gonna create this data set called MNIST, which is a data set for recognizing character for digits between 0 to 9. So there's images with digits. I'll show you how the data set looks like in a sec. So there's images with digits 0 to 9 in them that are handwritten, and there's 50,000 of them for training, 20,000 of them for testing, and 20,000 of them for validation. So there's the data set will be prepared when you run this command. I'll show it to you right now. And so basically you're going to use this data set for mini project 3 and also for 4, I think. So all you have to do is, once you import this, this is all wrappers that are meant to make these things very easily. So it's going to download the data from wherever the data is hosted, and it's going to set it up as it's going to be used by the Toolbox. And that's it. So it created a data set 27022. That's kind of an encryption key for the data set itself. So you'll need that key when you're loading the data set. Let me show you how it looks like. So I don't know where it should be. It should be here. Okay, so here it is. In this directory, 27022 is created, which has a bunch of parameters. It has test, train, and valid. Each one of them will have one batch of data. That's how this data set was designed. So the first thing I need to do after I have a data set is I need to create a input layer. So input layer is created with a data stream, which is basically the data set itself. For that, I need to specify what data set I want to use. So if you have multiple data sets that are cooked, you can specify which data set you want. So we want the data set that was created just now, which is 27022. The data set has 10 classes. It goes from 0 to 9, 0 through 9. I'm sorry, I made some mistake here. Oh, okay. That's a Python dictionary, so this is just a basic Python dictionary. So to create an input layer, I will use the add layer method. The layer type is input, and the parameters that I want to create to initialize the data set for this input layer are the parameters that I just created. Again, I'm making, okay. There you go. So that added an input layer. And you can check that we have added an input layer by checking the net layers. It created a layer 0, and that's the ID of the layer. The network also has this method called prettyprint, which will print on terminal how the network looks like. At this moment, the network has only one layer whose ID is 0. The output shape of a layer tells you what the layer is going to output, the size of the layer output. So this is a 4-dimensional array with 500, 128, 28 in its sizes. So what this means is there are 500 images. It's a grayscale image, so there's only one channel of image, and each image is 28 by 28 pixels size. Okay, so that's how you can check what's happening with the network. And what network do we want to build? We haven't built a logistic regression so far, right? We've only done linear regression. So let's do a logistic regression. To do a logistic regression, I need a softmax layer. So I'm going to add a layer softmax, and I want it to classify 10 classes. And that's it. Softmax layer is added, and So you now have two layers, 1 and 0, and if you see the network itself, if you print it, you have layers 0 and 1. 1 is connected to 0 and 1 outputs 500, 10. So it outputs a probability distribution of 10 classes for each of the 500 images. Okay, so that's what that means. Yeah?
Is it always necessary to specify the number of data sets in the training data?
The number of what?
Data set like 500?
No, the cook MNIST method that I first ran, it internally has a wrapper which creates it. So if you look at the Toolbox API, you can supply what is your batch size and everything.
Okay.
That's the 500 is basically mini batch size. There's 50,000 images and there's 500 mini batches. 500 images per mini batch. So there are wrappers for you to create how many ever you want. You can change it, and if you want, you can create one. Now that I said that, let me show you this, that the entire API of the Toolbox is over here. So if you go to the Toolbox documentation, all the kinds of layers you can have, all the kind of modules you can have, and data sets you can have, they're all here. The code is also here, so you can go and see how to do all these things. But this is just the Napoleon format documentation. So we have added two layers, an input layer and a class softmax layer. The next thing we want is an objective layer, the way we did backprop in class. So let's add a objective layer, and that's it. So we have an objective layer. So let's see the network again. So the network now has three layers. Layer 1 is a softmax classifier layer that comes from layer 0, and then layer 2 is supplied by layer 1, which has an output shape of 1. Why does it have an output shape of 1? Yeah? Yeah, so it's the average error for the entire mini batch. So the output shape of 1, if you remember the question from your exam or from the class, has a summation of I equal to 1 to n. If it is cross entropy, then there is something. If there is error, then there is something. But it's a summation over the n, and n is 500 in this setup. So that's one cost function. That's when you do backprop, the derivative is taken with respect to this one output and it's passed back. Okay. So now that we have the objective and everything, we need to create the backprop, the backpropagation system. There is one command on the net that does this. It's called cook, and that basically creates all the backprop, all the gradients, everything. You don't have to do anything, just run that. And it's going to set up all these other modules, which you will know in the next mini projects. When you do convolution neural network, the visualizer module saves nice filters, which you can look at and see how. Maybe we can see right now also. Let's see. So right now it's doing the backprop, which is doing the optimizer, which is setting up the optimizer for this. And there's all defaults. Your mini project is you will change the optimizer to do other things like RMS prop and add a grad, and you'll change learning rates of them. So let's train the network. So now that we have cooked, we just have to train, and it is running epoch 0. Even on a virtual machine, it's training pretty fast. And you can see that it prints out accuracy, it prints out the cost of every epoch, and I think it runs for about 20 epochs. I was hoping it will take like 10 minutes to run for 20 epochs. So training complete. It early stopped. I haven't really taught you what early stopping is, which I'll do in the next lecture. So it produces an accuracy on validation set of 86.56, and with a cost at 0.74. That's what it means. And once you're done, there is a testing set, so you can. Well, let me first show you how these outputs look like. So there is this method called layer activity, I think. Yeah, layer activity of, let's say I want to check the layer. Every layer has an ID parameter which will tell you which layer you're trying to access. And let's say I want to see the layer activity of layer 2, I think, right? So layer activity of layer 2 gives me this value. So what it means is, for the mini batch that's currently loaded on the CPU or on the GPU, this is the output of that layer, right? So you can check the output of each layer. So if I check the output for layer 0, I'm not going to run it because it's going to print a big matrix of 500 images. So let me just run shape. So that shape is kind of the way to find out what the size of the output is, and it gives me the size of the input itself. So if I run that for layer ID 1, it will tell me, actually let me run layer ID 1. So it gives me a huge matrix. What this means is so there's 10 values in each row, and there are 500 rows, one for each image, and this is the probability value that it belongs to that particular class. So in this case, it probably belongs to this class, which should be 8. The others I think are very low. So that's the probability distribution of the image over every class. And you can do this for how many other layers you have. So once, yeah.
Did you? See, I saw you add a softmax layer and a logistic regression layer.
Softmax layer is a logistic regression for my mini classes.
Did you have fully connected layers before?
No,
that?
I did not. I just had the input directly going to a softmax. It was a simple multi-class logistic regression.
Okay.
This is actually the same network for which we did the backprop by hand.
Okay.
The 3-layer network that we did backprop by hand, this is the one. We have images that go, so the image is basically a vector of 1 cross 784, because it was 28 cross 28 image. So its image is a vector of 1 cross 784, and softmax is a vector of 1 cross 10. Objective is just a scalar. So this, let's find out what this matrix size is. That should be interesting. So what he was asking is, how does that happen? Oh, sorry. So here's the softmax layer, and this has parameters W, and it also has parameters B. You can check that by checking what parameters it have. Oh, sorry. And you can also see what the shape of W is, which is 784 cross 10. So if I have 784 cross 10, I get an output of 10. Does that make sense?
So then this network doesn't have any hidden layers, right?
No, it just has, well, you can call the softmax layer a hidden layer because the objective is the one that we are seeing.
Okay.
But you can see any layer if you want, so no. Okay, so now the network is fully trained. We can test it on the testing set. All I have to do is run this test command, and it's going to show me a testing generalization accuracy of 85, and a validation was 86, so it's not overfitting too much. And these are the two, testing and the training. Validation accuracies are what you're going to optimize for in mini project 2. You're going to come up with for this. I don't know if it's the same data set. The data set that I want you to use is mentioned in the project itself. You will be given a data set which you can just run by one of those cook methods, and the network architecture is also there on the tutorial code that I've given you. All you have to do is change the learning rates, the optimizer itself, and I've described how to do that in the tutorial. And you will play around with learning rates, SGD, AdaGrad, or RMS prop, and polyak momentum or nest-of momentum with different values of weights for momentum. L1, L2 regularizer with different weights of regularizer. So there's about 15 parameters that you can change, and write one program which will have an optimal set of parameters which you think provides the best result. So you'll have to devise a strategy for changing all these variables, because if you change all of them at once, you won't know which one is contributing to the error going down. There isn't really one good answer. Different answers can be correct. So you need to do the dirty work and figure out. And this is how most of the deep learning works. We just have these things in hand and we'll just play around with them. So this will be good experience for you.
Is there anything on the data that we have, we can guess out that this is?
If you want, you can just print the data out and see. I'll show you how that happens right now. So okay, maybe I'll do it right now. So if you see the same directory, by now a visualizer is created, and that has a sample of the data. and I'll show you how the data looks like. So here's how the data looks like. It's a bunch of numbers that are handwritten, and you can do this for your dataset also. You'll be able to see it. And what's more interesting is what are the output activities of each epoch. So let's see the last epoch. Here's the output activity, which is basically the output of that layer. I think it's still opening. Which just looks like a bunch of numbers because it's just a probability value. The more interesting thing to look at is the filter itself. So we had 10 neurons for each of the softmax, and I'll show you how the weights of the softmax actually look like. And all of these will get saved down. So that's interesting, isn't it? Because the first neuron's job is to detect 0, the second neuron's job is to detect 1, the third neuron's job is to detect 2, and so on. So the neurons themselves adjust to how the generalized image of the entire data set looks like. The darker areas are applied different weights, and the brighter areas are applied different weights. So we are visualizing the weights of the neuron as an image. Isn't that interesting? And when you have multiple layers, you'll find that the first layer will extract some structures, and the second layer will extract more structures. And as and when we go on, we'll visualize all these things, and we'll find out how they look like. And from now on, the mini projects will involve a report where you'll write your observations on all these things. And one of the reasons why you can use this toolbox is all these things are already comfortably written in, so all you have to do is just call the methods and you'll get all these outputs. And you don't have to spend time writing all these code, you can just do the analysis part of, yeah.
So the input images were all scaled and in a way like they were all in the middle.
Yeah, they're all normalized. You can check the values of the input image. Let me see if I can show you. I think this data set is created in such a way that it normalizes everything. So if you see the API, there are ways for creating unnormalized data also. Let's see. I don't know. I have to see it. So this is the layer. So you can see the output. I think this provides the output if I'm not wrong. Or this. Yeah, we can just do that instead. So every layer has an output, should have an output. Oh, sorry. Every layer should have an output and an output shape. So that's the output shape, and you can get the output over here, which will just not work because it'll have to print a whole Tiano array. Let me see how to do that. Okay, so that's basically the images. If you want to see what the minimum is, you can just call the minimum method. Minimum is 0 and the maximum is 1, I think. Yeah. So the image was normalized between 0 and 1.
Yeah, mostly was scaled. So positional scaling, basically everything was on the.
Oh yeah, you can actually look at the image. The visualizer would have saved the image down, which is over here. So in this data set, the images are all in center. The character is written approximately in the center. Each image is 28 by 28 pixels, and the character is somewhere in the middle. And that's why the filters also look like that. So that's all you need to do for this mini project. I think I did logistic regression, so the mini project will involve, if you go to tutorials, there's a tutorial on multi-layer neural network. So you'll implement this. The number of layers you want to add is given over here. It's 800 nodes per layer. And also, if you want to set up an optimizer, there's a method which is provided here which has an add module optimizer, and this tells you how to change your optimizers. So you don't have to do anything, just change polyac to Nesterov and you get a Nesterov momentum. Just change RMS prop to Adagrad, you get an Adagrad optimizer. So that is simple enough. There is no real coding involved. The task of the mini project is come up with one of these architectures which will give you the best accuracy. Okay, so you're not going to do any coding. All you have to do is just change values here. Everything else is set up for you in this tutorial, and this tutorial also tells you how to set up these networks and how to write these commands and everything. Just come up with a network, come up with one file which will produce what you think is the best testing accuracy, best generalization accuracy. Also know that I will test on a separate set of data that I have. Okay, so I have a generalization set. I'm giving you training set, validation set, and a testing set, but I have a generalization set which you will not know. So you'll have to have that in the back of your mind. Any questions?